And I have my microphone on. Yes, the microphone is on. Everything should be ready. Okay, would you mind opening us up in prayer, please?
Lord, we just want to pray, Lord, in Jesus' name. You would bless our time together, bless our fellowship, Lord, bless, Lord, this study, Lord God. We pray that you bless the Bible college class. Lord, anoint our teacher, Lord God, the words to speak, Lord God. Father, we just pray, Lord God, that you give us ears to hear and, Lord, eyes to see. Give us understanding. Lord, we pray, and Father, we just pray, Lord God, over the technology, Lord.
Please.
Lord, pray, Lord, that you would bless this Bible college for the work they're doing. In Jesus' name.
Amen. Well, I'm going to back up just a little bit. Last time we were talking about chemistry, and I rushed through some of the history of chemistry, and I think it's pretty neat the way some of this stuff developed. So the first guy that came up with an idea that there was such a thing as atoms was Democritus. And unfortunately for him, he was shortly before Aristotle. So Aristotle came along. He said, no, no. Democritus's ideas said that there had to be empty space in between atoms. And no, Aristotle, say there couldn't be any such thing as empty space. So therefore, nobody believed poor Democritus. Well, then, along the way, you had the alchemists who came along. They weren't concerned very much with theoretical chemistry, but they were trying to figure out how to get gold out of stuff. Like there was one guy who got a whole bunch of soldiers to donate buckets of urine because he said it's gold colored and so it must have gold in it. Well, he later was able to extract phosphorus, pure phosphorus for the first time. Um, he couldn't duplicate his work, so he sort of died penniless. But there was a guy that came along, and after it was all purified and the urine was gone, he bought this stuff. And if you take phosphorus, you can write on it, and it'll glow in the dark. And so this other guy played like he was a magician, and he did all sorts of stuff to make money. Okay, then the guy that really started the modern chemical theory was John Dalton. It had been thousands of years since anybody paid attention to poor old Democritus, but Dalton said, oh, come on, that makes sense. There has to be some lowest whole number of ratio where we put together two of these and one of those. And this was confirmed by experimentation. With Democritus, it was just theory, but no, Dalton, he said, okay, let's try two of this and one of those, and okay, we have almost nothing left over. Three of these and one of those, we got a lot left over. One and one, we got a lot of the other left over. He said, come on, down at the lowest level, there must be a small particle that's combining, and he called it the atom. So he came up with some ideas about the atom, and part of it was right and part of it was wrong, but not that much wrong. He said all atoms of the same element will be identical. Later we found out no, they can vary slightly in the mass. He also said that matter was made of indivisible atoms. You couldn't divide it into anything smaller. Well, later on, we discovered protons, neutrons, and electrons. But still, it wasn't that far off. So we didn't just throw it out entirely. Like the ancient Greeks believed everything was made out of, you remember this? Earth, air, fire, and water. Well, that's been thrown out. It was just so far wrong. Was Dalton right? Well, he was a lot less wrong. Are we all the way right? We don't know, but we're a lot less wrong. We try to get less and less and less wrong all the time. And then Avogadro figured out that any two gases in the same container are going to have the same number of atoms. So he worked out the relative atomic weight, which was a key concept later on in Mendeleev working out his periodic table. Mendeleev was a Russian. He was actually a science teacher who became a chemist. I think that happens a lot where the science teachers have to have a general view where the scientists may focus on one specific aspect of science. So Mendeleev is a guy that came up with a periodic table for the first time. There was another guy, a German guy, who was working on it, but he didn't make any predictions. Mendeleev said, okay, there's three missing places here. We're going to find elements that fit in there. And he was right. So he's given credit for the periodic table. Okay, so then various people tried, I don't know why, but when Volta invented the battery for the first time, various people tried hooking up a bunch of batteries to get a high voltage electric current. and they ran it through a gas at low pressure. Why? I don't know. Why did you climb that mountain? Because it was there. So as people would run an electric current through a gas at low pressure, they'd see a glow. And you could tell it was not pure energy because it was in a sealed up container, but if you put a magnet near the outside and turn the magnet, the beam moved also. Energy doesn't respond to magnetism, but particles do. So Thomson's a guy that got credit for discovering the electron, even though a whole bunch of people worked on it. And then later on, his student, Ernest Rutherford, wanted to prove that his professor was right, kind of like butter up the teacher. Well, Rutherford wound up proving that his professor was wrong. Rutherford was no slouch himself. He also won a Nobel Prize. He discovered the alpha and beta and gamma types of radiation. A little before him, Henri Becquerel, Marie Curie, they had discovered that radioactivity existed, but they didn't break it down into the types. But Rutherford did break it down into alpha, beta, and gamma radiation. So he used a source of a radium source to send alpha particles through a gold foil. And he was expecting that it would just kind of go right through. As it turned out, some of the particles bounced right back. And the way you could tell is around the gold foil, there was a screen coated with a phosphorescent material. When struck with an electric charge, it would glow. So you could see, yeah, most of the particles did go right through, but some of them deflected at severe angles and some even bounced almost straight back. So that meant there had to be, instead of just a spread out type of positive charge, it had to be concentrated in a small area called the nucleus. Well, he didn't know where the electrons were when they were not flowing, but he said they're just somewhere around. Later on, others came along and said, okay, let's do a better idea than that. Oh, along the way, there was a guy named Henry Moseley. He was a British guy, and at the time, nobody had ever heard of an atomic number. That's the number of protons. Well, Moseley was a student of Ernest Rutherford. And so he realized that different elements have a different charge in their nucleus. So he called it the atomic number. Rutherford had discovered the proton. Well, Moseley went a little past that and he came up with the idea that multiple protons are going to give you different atomic numbers. Of course, the problem there was World War I broke out and he was killed in the Battle of Gallipoli. He was a brilliant chemist. He probably would have made a lot of progress, except that he died. Well, and then to try to explain where the electrons are when they're not flowing through your high voltage electric current through the gas, Niels Bohr, a Danish guy, he was a brilliant mathematician. He came up with the idea the electrons must be orbiting at specific distances from the nucleus, and each distance has a specific exact amount of energy. And so if the electron gets some sort of energy applied, like electricity, ultraviolet, X-rays, it jumps to a higher energy level. But when it drops back down, it's going to send out a little particle of energy called a photon, which shows up as a color. So he did some calculations with hydrogen, which has only one electron, and it was perfect. Worked wonderfully. This was the beginning of quantum mechanics, because if you've ever heard the term a quantum leap, quantum is Latin for how much. A quantum leap is from here to here with nothing in between. Like if you're climbing stairs and you got a step here and a step here and a step here, you don't stand in between. You stand on this step or that step or that step. Well, likewise, quantum mechanics says that the electrons has either this energy level or this or this or this, and nowhere in between. Well, it worked perfectly for hydrogen, but no other element. All of the elements emit colors when you send electricity through them, or ultraviolet or gamma radiation, some high energy source going through a gas. So hydrogen was nice and predictable, but all the others, helium, fluorine, chlorine, bromine, they gave a bunch of colors, much more than what you would have expected according to Bohr's model. So Bohr, not Bohr, but others expanded on his idea and said, okay, there must not just be the main energy level. He discovered 7 principal energy levels that were responsible for all the colors you got out of hydrogen. But other people said, there must also be sub-levels that are close to those. And so the electron doesn't exactly go into that place all the time. Maybe there's another step a little bit lower, step a little bit higher. And so this led to further developments in quantum mechanics. And it also led to the realization that electrons are particles and waves both. Is an electron a wave or a particle? Yes, it's a wave or a particle. When it comes out of an atom and it's flowing in an electric stream, it's a particle. When it's in an atom, it's a wave. So other people worked with this and they came up with ideas about how the various colors would be produced according to what energy levels there are. And it's pretty complicated. If you ever study on electron configuration, it can be pretty confusing, but it does a very good job explaining. So then Erwin Schrödinger came along and he worked out the mathematics for how would you describe all of this. In science, you want to get into mathematics. And Schrödinger derived his wave equation, and I have no idea how you go about getting that. It's way too advanced for me. A lot of PhD scientists would have a hard time seeing how he derived it, but he was a brilliant mathematician. And he showed that the behavior of real things, protons, neutrons, electrons, behavior of real things could only be described with imaginary numbers. So it's like the thing is here, disappears out of real space, reappears over here. Wait, how did it get there? It didn't go through real space, it went through imaginary space. So imaginary numbers are necessary to explain the behavior of all of these things. So an electron is actually not a particle when it's in an atom. It's like a throbbing wave. And there's a bunch of electrons in most atoms. So you have all of these throbbing waves overlapping with each other, doing all sorts of interesting things. So I want to show you guys, those of you that are watching this video, you should go to that link, youtube.com/ and all that, and look for the Atom Song. I'm going to play it for you right now. I hope it comes across on the audio, but it mentions about some of these guys that did all of the stuff. You won't see the video on here, so you got to go look that up. Start at about 30 seconds. Dalton, Thompson, Rutherford, and Bohr, Wittenberg, and many, many more. Use them. Was a weird Dalton did experiments, said I think it's clear. Atoms are tiny indestructible spheres. Thompson worked with cathode rays, said I disagree. A plum pudding model makes much more sense to me. A new chapter in atomic theory started to unfold when Rutherford played around with atoms made of gold. When a few of his alpha particles came bouncing back, he hypothesized the nucleus had knocked them off the track. Dalton, Thompson, Rutherford, Schrödinger, and Heisenberg, many used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Bohr saw spectral lines for hydrogen and said it seems to me electrons move in orbits with specific energies. Heisenberg said, forget it. There's no way to know the orbit or a path where the electron's gonna go.
Schrodinger used lots and lots of fancy mathematics, made a model of the atom based on quantum mechanics. It has orbitals, and those are based on probability. The atom is a fuzzy blob of pure uncertainty. Johnson, Thompson, Rutherford and Bohr, Schrodinger and Heisenberg, and many, many more use their brains to venture in the realm of inner space and found the world. The atom was a weird and wondrous place. Dalton, Thompson, and many more use their brains to venture in the realm of inner space. Found the world of the atom was a weird and wondrous place.
I like that video. I think it does a pretty good job of summarizing some of the major contributors and contributions. It did leave out the neutron, though. That was a guy named James Chadwick. Chadwick was a very shy guy. He enrolled in Cambridge University. He wanted to be in mathematics, and they stuck him in physics, and he was too shy to complain. Well, it turns out he wound up getting a Nobel Prize too. He's the one that discovered the neutron. Other people had said there's got to be more to it than just the proton and the electron, but nobody could discover it. He did a very low-tech experiment involving paraffin wax. I don't know what the details were, but he discovered, oh yeah, there's this thing called the neutron. And other people immediately began to use that to split atoms. And Chadwick said that he realized from that point that atomic bombs were not only possible, but they were inevitable. So for the rest of his life, he said he had to take sleeping pills to get to sleep. Imagine that if you knew I personally have opened the door for atomic bombs. That'd be kind of a tough thing, right? Of course, it did end World War II, but wow. So the Manhattan Project started up in the Manhattan region around New York. Chadwick was one of the principal British scientists on the project, and there were a bunch of other ones. Einstein was not directly involved other than writing a letter to the president saying, hey, Hitler's working on this. You need to get busy. So here's where we were last time. Moving on. If there's one atom that splits, this is supposed to be a uranium atom, uranium-235. If one atom splits, it's going to turn into things like barium and krypton, not necessarily those two, but the total mass is going to add up to the same within a tiny, 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 tiny little bit. But that tiny little bit releases a lot of energy. Einstein had an equation, E equals mc squared. That is, the amount of energy you get out of something is the amount of mass you convert times the speed of light squared. So for one atom, it's not that much. But if you just take one little chunk, you've got quintillions of atoms in that one little chunk. And so if you get a chain reaction going, you can destroy Hiroshima and Nagasaki. And of course, we have bombs that are far more powerful than that. There were a bunch of scientists that were involved in this, and they succeeded. They built new towns from scratch at Oak Ridge, at Los Alamos, I think at Sandia, and the people there were working on one part of an atomic bomb, and they didn't know. They just know, I make screws for a living. What's a screw go to? I don't know, but eventually they were put together into the atomic bombs. And actually, the atomic bomb was the result of splitting a uranium atom. So when it's finished, you have a tiny bit less mass than when you started. That tiny bit was converted into energy. But after that, people figured, okay, let's see if we could go the other way. Instead of splitting an atom, let's fuse two atoms together. So this is called a hydrogen bomb because you take two hydrogens and you smush them together into helium, and you lose a little bit of mass, but it's a much higher percentage. And so a hydrogen bomb is far, far, far more powerful. To set off an atomic bomb, you need conventional explosives like TNT. To set off a hydrogen bomb, you have to get the temperature up to millions of degrees. So you have to have multiple atomic bombs to start the hydrogen bomb going. And if anybody ever heard of a TV program called SpongeBob SquarePants, you heard of that? Okay, when the creators of the show were writing it and trying to figure out all of the background behind it, they happened to hire a marine biologist to make sure that all of the characters, all the creatures were moving, kind of reasonably for sea creatures. And so this marine biologist asked them, "Where are you going to have this set?" They said, "We don't know." He said, "Why don't you put it at Bikini Bottoms?" Because the first hydrogen bomb test was at the island of Bikini, and it was far more violent than the atomic bombs. And when it went off, it was so dramatic that, somebody said, "I'm going to make a dramatic new style of bathing suit called the bikini." And there was so much radioactivity left over from setting off the atomic bombs that set off the hydrogen bomb that the US Army just bulldozed all of the dirt into the ocean at Bikini Bottoms. And the ocean bottom is incredibly radioactive. And that's why the guy said, "Look, you got your excuse to have all these characters do weird stuff. They're mutants because they're living around all this radioactivity." So that's why SpongeBob is at Bikini Bottoms. See, you learned something from this class, didn't you? Okay, so the project to develop nuclear fission for military use began unofficially during the earlier parts of World War II before the US got into it, but Britain was under constant attack from the Nazis. And so anyway, the US got involved behind the scenes, and they decided, when the US entered the war, let's move it over to the US because Germany can't reach the US, where if we're doing it in England, they could fly over and drop bombs on us. So when J. Robert Oppenheimer, the guy that was in charge of the Manhattan Project, when he watched the first successful test of the bomb, who was codenamed Trinity, to make sure it would work, it went off about 20 miles away, and he and everybody else was watching from bunkers, and he saw that thing go off. It was far greater yield than they expected. And I mentioned last time that he quoted one of the Hindu writings that said, "I am become death, the destroyer of worlds," because he knew, I made sure it all worked. It's on me. Well, anyway, later on, we found some other uses for nuclear energy, some peaceful uses. Anytime you want to produce electricity on a large scale, the way we do it now, you can do photoelectricity with sunlight, um, but anyway, the most effective way to do it is by spinning giant magnets past giant coils of wire. And when you do this, you're going to produce electricity. So you have to spin the magnet somehow. You put it in a turbine, and a human being would be, like half as tall as one of those things. You have something going past the turbine and spinning it. It can be the water coming down a mountain from a river or reservoir or something like that. It can be tides coming in and out from the ocean. It can be burning coal, burning oil. But the cleanest form of energy we've got so far is nuclear energy. Now, there have been a grand total of, I think, 3 accidents, and they were bad, but still, it's by far the safest form of energy, unless you live right there. If you do, then you'd say it's not very safe. So that's one of the things. You use the most powerful energy source known to mankind to boil water, and that spins a turbine and produces electricity in large amounts. So, people right now are all excited about got to get an electric car because they have no pollution output. Well, wait a minute. When you charge them, where's that electricity coming from? If it's coming from a nuclear power plant, okay, no pollution output, but most power plants are not nuclear. So to charge the thing, you got to have something burn somewhere. So maybe it's not burning right at your car, but it's burning somewhere else, and it's still polluting the environment. Best thing is just walk or get roller skates. That another thing that these are used for, space probes can use something. It's a heat engine called a Stirling engine. And as long as you have magnets moving past wire, you can get electricity. So they use the heat from a radioactive material to cause an expansion. The heat's radiated out into space. It contracts, it expands, contracts, and you could theoretically get thousands of years worth of use out of a small radioactive sample on a space probe. And then it's used in medicine for obtaining diagnostic images. It's also used for cancer tumors. You bombard a cancer tumor, you send a beam of gamma radiation through the tumor, and it's going to kill everything on the way in there and on the way out. But the alternative is death. So, okay, we're willing to do that. And there's another variation of that is there's a very localized tumor that has not spread. You can take an alpha radiation source and inject it with a needle right into the tumor. And as the alpha particles come out, they'll kill the tumor from the inside out. But the problem with that is a lot of times before you detect the tumor, before you detect the cancer, it's already spread. So it's not always that useful. In food preservation, the thing that makes milk rot and all of that is the bacteria in it. So you take your food and you put it under intense radioactivity and it's going to kill everything in it. So when you drink it, you're drinking little bacteria, but they're dead bacteria and they don't hurt you. If they're live bacteria, they'll make you sick. And also insects, you're eating dead insects, but it's just extra protein. So those are some of the peaceful uses of nuclear energy. Um, and of course, nuclear reactors are used on a lot of military vessels. So I don't know, is that a peaceful use or not? So far, we haven't learned how to control nuclear fusion. Nuclear fission, splitting the atoms, yeah, we've got that pretty well down pat. Okay, and this was a lot of stuff, so I'm going to go back over. At the end of the chapter, I have review questions. So here come the review questions. If I could find them. Here they are. Yeah, the ancient Greeks believed everything on earth was made of what, and what? Yeah, earth, air, fire, water, earth, wind, fire, and water. And of course, they had the musical group back in the 70s, Earth, Wind, and Fire. Oh, they were so good. And then I'll get to the answers in a minute. Suppose you see a bag of bread that says contains no chemicals. Should you trust the label? Nah. What does the second law of thermodynamics have to do with how the sun's energy came together in the first place? How can chemists tell something is an element? How can they tell it's a compound? How can they tell it's a mixture? Difference between an atom and most types of molecules. The way to find out the chemical properties. What does a chemical change cause? Most common state of matter in the universe. Most elements on the periodic table are what? I'm going through this super fast, but just look at the review questions at the end of the chapter. That's what I'm getting to. On the left side of the periodic table, there's a tendency elements have concerning holding electrons versus on the right side. The Bible hints at something about the strong nuclear force that holds everything together. The shell of electrons in an important in chemical. There's one particular shell. Two examples of common types of chemical reactions. Molecules have a three-dimensional shape because of something to do with electrons. Okay, the first reported person that proposed the idea of atoms. Why was this discarded for about 2,000 years? And who was the person that proposed a modern theory? Who's given the credit for developing the periodic table, even though other people worked on it at the same time? Could you turn the temperature down a few degrees, please? And what led Thomson to conclude there must be particles smaller than an atom? What model did he propose for where they were when they were not going? And what did Rutherford use to discover that an atom had a nucleus? What is there about the size of the atom and the wavelength of light that doesn't allow us to see atoms even with the most powerful microscopes? You got these all? You're going to be able to just spout them out? No, in just a minute we'll get to them. How did Bohr explain the colors? How can science determine what elements are in stars without even going there? How does Schrodinger's work fit with Hebrews 11:3? And how did I left out the word did. How did Chadwick's discovery of the neutron affect him personally? And some non-military uses of nuclear energy. Okay, first, the ancient Greeks thought everything was made of earth, air, fire, and water. If you see a bag that says contains no chemicals, then it's an empty bag because everything is chemicals. It's all stuff off of the periodic table. The second law of thermodynamics says that energy tends to spread out rather than flowing together. And of course, the first law says there's no known process that can bring energy into existence or make it go out of existence. The second law says it tries to spread out. So here's what the second law has to do with how the sun would have first come together. There's no known process that would force the energy to come together. Right now, the sun is gradually radiating all of its energy out into space, as are all of the stars. Well, what would have started the process in the first place? There is no known answer. It's an unknown answer. It can be an unknown natural process or an unknown supernatural process. You can't test it either way. How can chemists tell something is an element? They try to break it down into simpler parts. Um, if you can't do it by anything short of a nuclear process, nuclear reaction, then it's an element. How can you tell it's a compound? You can break it down into simpler parts with chemical processes, for instance, the addition of acids or electricity or some other reactive type chemical. How can you tell something's a mixture? Well, a mixture is relatively easy to separate. You can use physical processes, sifting, boiling, magnets, things like that. The difference between an atom and most types of molecules is that most types of molecules are the smallest particles of a compound. There's 7 elements that only exist in a molecule of 2 atoms each, but the other 111 are individual atoms. So generally, a molecule is the smallest particle of a compound rather than an element. And how do we find out the chemical properties? Try to get it into a chemical reaction. If it reacts, that's a chemical property. If it doesn't react, that's also a chemical property. A chemical change is automatically going to cause a change in the formula of the stuff. So if I have water H2O and I do a chemical change, it's not going to be H2O anymore. The most common state of matter in the universe is a plasma, which the stars are made out of. And of course, we have to conclude this logically because we haven't been to any stars. You'd have to go at night, otherwise you'd burn up. Most of the elements on the periodic table are metals. Even though we don't think of them, a lot of them, yeah, those are metals. The tendency of electrons on the left side of the periodic table is much weaker to attract electrons. Those on the right side is much stronger to attract electrons. So the ones on the left tend to give up electrons to the ones on the right, which rip them away. The ones on the right are bullies. And the ones on the right are actually smaller atoms than the ones on the left. So the little ones are the bullies. I always used to get one of the smallest girls in my class to come be the bully and take away the electron from the big guy like Anthony. He'd be holding an electron and I'd say, you act like one of those non-metals. She'd go get it away from them. The little ones are the bullies. Okay, the strong nuclear force. Why don't all of those protons in the nuclei fly apart? We don't know, so let's give it a name. Let's call it the strong nuclear force. Every atom in the universe that has 2 or more protons ought to fly apart, but they don't. So, okay, sure, that's the strong nuclear force. This is what the Bible said. I like the English Standard Version. King James says consist, but English Standard said hold together. The strong nuclear force is not a purely physical phenomenon. Colossians 1:17 says of Jesus, he is before all things, and in him all things hold together. So this man who walked around Galilee for about 3.5 years, well, for 33 years or so, he was God. How hard would that be? This guy you've been hanging out with for 3 years to realize, oh, he made the universe. That's a mind-blowing idea. Okay, so the shell of electrons in an atom that's most important is called the valence electrons. That's the outermost electrons. The inner electrons don't generally do that much, but the outer ones, you're trying to get 8 electrons around the outside of the atom. If you've got 1, but there's another shell closer in that has 8, the atom is very happy to let the 1 go. So it says, I got my 8 now. And if an atom has got 6 electrons around the outside, like oxygen, it says, I want two more electrons. Give them to me. And it's going to take them. The most reactive element there is fluorine. The second most is oxygen. There's a bunch of common types of chemical reactions. There's hundreds, but when two things come together into one thing, like hydrogen and oxygen into water, that's a synthesis. Or if you break apart water into hydrogen and oxygen, that's decomposition. You can have single replacement, double replacement. Things can burn completely where you get carbon dioxide, or you can have incomplete combustion where you get carbon monoxide. Carbon dioxide is also bad for you because you need oxygen, but carbon monoxide actually actively attacks your blood to take another oxygen out. And one of the places that your blood goes through that has a densest concentration of cells is your brain. So carbon monoxide gets in your brain and it starts yanking away the oxygen atoms out of the brain and killing the cells. Okay, the thing that causes molecules to have a three-dimensional shape rather than being flat, atoms try to have 8 valence electrons around them. Well, the electrons for some reason work in pairs. I don't know why they don't work in apples, but they work in pairs. That was a joke. Um, so there's a theory that explains how this works called valence shell electron pair repulsion theory, VSEPR theory. And it says, okay, they work in pairs. And the pairs try to get as far away from each other as they possibly can. So I can't illustrate too well, but I'm going to put 1 foot forward, 1 foot back, one arm up left, one arm up right. So my limbs are as far apart as they can be. That's what the electrons try to do in the atom, go in 4 different directions. So something hooks here, hooks there, hooks there, hooks there, and you get a three-dimensional shape. The first reported person to propose atoms was Democritus. I always used to give my students a test question, and I'd give them a choice: Democritus, Republicanus, Independentus. Most of them got it right. It was discarded for about 2,000 years because Aristotle, the big guy, he said, nah, there couldn't be any, I left in spelling, there couldn't be any empty space between atoms, so therefore there couldn't be atoms. The first person that proposed the modern theory, Dalton, Thomson, Rutherford, and Bohr. Okay, John Dalton, approximately 1800. He was actually a chemistry teacher rather than a chemist. And the person given most credit for developing the periodic table was a Russian guy, Dmitry Mendeleev. Thomson was working in England, and he noticed, not just him, but people noticed that if you ran a high voltage current through a gas at low pressure, there was going to be a stream of particles that became visible, and all of the gases gave the same result. So it wasn't just that hydrogen had this thing, but no, helium did, chlorine did, fluorine did, bromine did. Every gas you could put in there gave exactly the same results, even the ones that don't get into chemical reactions, like neon and so forth. That's why neon lights glow particular colors, because of the electron arrangement in neon. So Thomson said, okay, when the electrons are not flowing through, where are they? They must just be stuck around the outside of the atom. So the atom is like a blob of positive charge. And in England, they have a dessert they call a plum pudding. It's a raisin pudding. So he said, that's got to be what it's like. They're just kind of sitting there. Well, Rutherford came along and said, okay, I want to prove that my professor is right. No, I proved he was wrong. Rutherford and his colleagues shot alpha particles from radium through gold foil. And gold was chosen because you can beat it extremely thin, just a few atoms thick. It's one of the most malleable of the metals. And they found out that, oh yeah, look at that. Most of the particles did go straight through, but some of them bounced straight back. And the only way to explain that was that the positive charge must be concentrated in a very small area, the nucleus. So the reason we can't actually see this is because the size of the atom is thousands of times smaller than the size of the wavelength of light. So light is a wave like this, okay? The atom's like a grain of sand as compared to that. You can't see any details of it because it's just way too small as compared to light. So how did Bohr explain the colors? He said that The electrons must be orbiting the nucleus at specific distances that matched with specific energy levels. The electron could only move in distinct jumps, quantum jumps, and each one of those would release or absorb energy that corresponded to a specific color. So why is the grass green? Because the grass takes in all the colors of light, and the only one it doesn't use is a green. Get that trash out of here. I don't want that. That's the only color that the grass doesn't use is green. So how can scientists determine what elements are present in the stars? By analyzing the spectrum of light. In the laboratory, we've been doing this for, I don't know, at least 150 years or so. I don't remember the guy's name that first did it, but it's very, very well known. Okay, if it's that pattern of colors, it's hydrogen. That pattern is helium. So we point a telescope at a star and we split the light out through a prism. Oh, that's hydrogen, that's helium, that's lithium, and so forth. So it's not just guesswork. It's comparing to 150 years worth of laboratory observations. And then, anybody remember what Hebrews 11:3 says? Schrodinger, from what I understand, was not a Christian. He was kind of a nasty guy. But his work, Hebrews 11:3 says, by faith we understand that the things which do appear were made of things which do not appear. Okay, Schrodinger showed mathematically that the things which do appear, matter, are made of things that do not appear, waves. I think that is so cool that the Bible predated quantum mechanics by 2,000 years. People say, oh, that's just an old fairy tale book. No, it's never had to be revised. Chadwick's discovery of the neutron affected him personally. He couldn't sleep without sleeping pills for the rest of his life. And some of the non-military uses of nuclear energy would be electric power generation, medical imaging, cancer treatment, food preservation, things like that. Okay, so far, so what? Moving along, let's get into our next topic. I'm trying. Okay, as a reminder, these things are on the Moodle, and I also have a website, creationrevolution.net, and every time I make an update, I put it on there, and then I send it along to Jared at Legacy, so you can get it either place. So on the creationrevolution.net, use the Creation Science Lessons US and Overseas link. Okay, let's talk about the origin of life. This kind of is a natural flow from chemistry. Now remember, we started out a few weeks ago talking about astronomy, which is the beginning of the sciences, and then we got into physics. Why and how do things move? And then we got into chemistry, which was last time and then part of this time. Okay, so everything in the universe operates according to the laws of physics. But then when you get down on a smaller level, chemistry can only operate within the law of physics. Well, on a smaller level, biology can only operate within the laws of chemistry. So let's talk about where life came from. There are people that talk about evolution as being historical biology. Well, I think that's a pretty arrogant thing. It's not biology. Empirical has to do with things you can determine by experimentation. They're going on in the present, observable, repeatable, testable. So-called historical biology, well, it tries to explain how did things get to the way they are now by appealing to something that happened before human beings were here to observe. So we're making up stories from the unobservable past to try to explain the observable present. So the kinds of biology that have to do with what's going on right now would be botany, which focuses on plants, zoology, which is animal life in general. You have marine biology, ichthyology, which is fish, ornithology, which is birds, microbiology, molecular biology. at the cellular and molecular level. Genetics and reproduction also have to do with the cellular level. Physiology and pathology have to do with normal and abnormal functioning of organisms. Ecology has to do with how things relate to their environment, how they interact with it. But then the so-called historical biology is evolution. It tries to explain, apart from God, where did things acquire the characteristics that they have today. So I believe that the Creator put certain features into living things. Why? Because he wanted to. He doesn't have to explain to me why. In the book of Revelation, it says that all things were created for his pleasure. Okay, so I don't have to explain it. I accept that. Now, if somebody doesn't accept that and they say, no, I just can't believe in God like that, you better hope you're right at the end of your life. Because if you say, Pascal's wager, if I say there is a God and there is a God, I do well. I have the potential to be with God forever. If I say there is a God and there is not a God, it matters not, because I'll go through my life expecting to meet God. And at the end of my life, I'll say, here I come, Lord, and I'll lose consciousness and never regain consciousness. So I'll be no worse off. On the other hand, if I say there is not a God and there is not a God, it matters not. I'll go to the end of my life and say, oh no, I don't want to die. I can't fight it anymore. And I'll lose consciousness and never regain consciousness. But if I say there is not a God and there is a God, God help me. The Bible says that those that would come to God must believe that he exists. In other words, no atheists in heaven. So a person like that would go through their whole life fighting against God and refusing to believe, and they come to their deathbed and they say, I don't want to die. I don't want to die. Oh no, but I can't fight it anymore. And they die. And a few seconds later, they wake up and go, who are you? That would be the scariest thought imaginable to me. So I can't prove there is a God. Somebody else can't prove there's not a God. But really, the so-called historical biology is an attempt to explain things apart from God. There are some people that say it's just purely natural processes. That would be atheistic or materialistic evolution. There are other people that say, well, I believe that God wanted evolution so much that that's the process he used for his method of creating. Well, where'd they get idea? From the atheists. The idea of evolution has been around for a long time. The ancient philosophers, Empedocles, for example, around the time of Aristotle, they believed that humans evolved from fish. They didn't say where the fish came from, but carrying out logically, the fish had to come from something and eventually from non-living chemicals. So what they were trying to do is explain everything apart from God, from an all-powerful, intelligent God. They didn't believe that Zeus created the universe. They really didn't know who did. Somebody. While the Bible says who did it, it was God, our Almighty Father. So there are theistic evolutionists that say, well, I guess God did it this way. Why do they believe that? Because that's what the atheists said. If you believe what the Bible says, if you admit you're a young earth creationist, you're going to be thought to be an idiot in scientific circles. Well, I don't care. Call me an idiot. I'm a fool for Christ. Whose fool are you? I'm about to be 70 years old. It doesn't really matter if people make fun of me anymore. But there are some people, they just don't want to be thought to be foolish. So they say, well, okay, the evolutionists must be right that evolution was there, but still, I want to believe in God. So let's say God was guiding the whole thing. What they would say would be, for instance, that there was an evolving series of ape-like creatures that were becoming more and more and more and more human. So it had been hundreds of thousands of years, millions of years, and God's looking down from heaven saying, no, not yet. No, yeah, a few 100,000 more years. Not yet. And eventually God looks down and says, good enough. Okay, zap, you're human, you're Adam. Female, zap, you're Eve. Well, that's not what the Bible says. And the Bible specifically says that humans were created distinct from the animals. That's because God wanted someone who was in his image and likeness. So let's think about what some of the overall trends in the universe would be. You've probably heard of evolution before. Never mind who or what might be responsible. The basic idea of evolution is that things began in a disorganized condition and later became more organized, more complex. And there was an unlimited amount of diversification. So there's only two possibilities. Either the universe was less complex than it is at present, or it was more complex than it is at present. So when you say the word evolution, a lot of people are going to think of things like fossils and ape men and dinosaurs and Darwin and other concepts that sound scientific. But there's also a whole lot of religion to that. What's the meaning of life? Why are we here? That's religious. So you have to deal with that if you believe in evolution also. But ignoring that, we could just say, okay, what were the conditions at the beginning? If evolution is right, things have been getting more and more and more complex. That is, it was initial disorganization and things have been getting more complex. So to put it the easiest way, everything went, oh, everything went from simple to complex. That's evolution, simple to complex. Now, on the other hand, when you say the word creation, most people are going to think of what? Adam and Eve, Garden of Eden, serpent, forbidden fruit, things like that. Yeah, that's certainly part of it, biblical creation. But let's remove all of the religious aspects and say, what were the conditions have been? At the beginning or at the end of the creation week, then the universe was at its maximum organization and complexity. God looked around, he said, it's very good. Ever since then, it's deteriorated. So the initial conditions would have been complexity, and later there would have been deterioration and a certain amount of diversification, not unlimited, but a certain amount. So rather than everything being from one common ancestor, as evolution would say, there would have been, instead of one evolutionary tree, a whole forest of life. At the very beginning, God created everything to reproduce after its kind. You had the human kind, the dog kind, the cat kind, and the cat kind is pretty big. You know, a lion can breed together with a Persian cat. It's going to be a little uncomfortable for the Persian cat, but you know, you could do it, artificial insemination. They have similar enough DNA that it'll work. And horses and donkeys and zebras, you know what you get when you breed a zebra with a horse? I'm not making this up. It's called a zorse. And if you breed a zebra with a donkey, it's called a zonkey. They're the same kind. They've been separated out for long enough that they've diversified into different breeds. So we would believe that there would be a forest of life. That is, all life came from multiple ancestors and they were already complex. Then they could have diversified as time went on. So like maybe here's the zebras and here's the horses and here's the donkeys. But one thing is not going to jump across and connect to something else. So as a friend of mine used to say, when you have cats and you have dogs, you don't have dats. Although at the Superdome, they always hold up signs that say, who dat? Those of you in Chicago, that's just one of the things about New Orleans. The New Orleans Saints are who dats. Okay, so where did life come from in the first place? There are some people that try to bypass the question of how life gradually evolved, increased in organization by skipping the beginning. Well, you can't do that. If things went from lifeless chemicals to living things and then more and more and more complex and organized, you got to go back to the beginning. So at one time, it was thought that living things could arise spontaneously from decaying vegetation and rotting meat and so forth. There were experiments done, and the most famous was Louis Pasteur, who showed that without contamination, there were no scavengers such as flies that would appear. Previously, people thought that if you have rotting meat, it's just automatically going to produce flies. If you had dirty rags, they were automatically going to produce mice. Well, Pasteur did experiments where he showed if I boil broth, which normally will rot when left out, exposed to the air, if I boil it and leave it in the flask and there's a curved part, they call it a swan flash, that goes down like that, so that any air on the outside is not going to make its way around the curve and get in there, and it would keep indefinitely. Now, as soon as you open it to the air, little microorganisms would start to grow into it. So it's accepted that Pasteur conclusively disproved the idea of spontaneous generation from rotting things. So the discussion really has shifted, instead of from decaying material to lifeless chemical elements on the early Earth. Well, as far as we've been able to determine, everything is made of the same elements on the periodic table. I know on Star Trek and places like that, sometimes they'll have shows where they say, oh, it must be um, out in space, there must be silicon based. Well, on Earth, everything is based on carbon, every living thing. And in fact, out of all of the 118 elements known on the periodic table, 90 known in nature, the only one that'll form long chains is carbon. So if you're going to have complex life, it has to be based on carbon. I had a discussion with my uncle, who was a medical doctor, one time. He said, maybe it's based on silicon. No, carbon is the only thing that'll form the long chains you need for proteins and DNA. So it has to be carbon based. So you're going to have carbon in there somewhere. Even the simplest cell requires at least 6 elements. Every living thing known is made out of cells. So even the simplest ones require 6 elements. When you go shopping to put together living things, bring along your Chnopsing list. CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So that's, somebody took a picture of Louis Pasteur. Photography had been invented by then. So how did life begin? According to the idea of initial complexity creation, then life should be far too complex to be the result of just purely natural processes. And we would expect, since God created the earth to sustain life, that the early earth should have had conditions that were not too different from what they are at present. Now, if you believe in evolution, though, you would say that natural processes should be sufficient to produce life with no supernatural intervention. And at present, the chemistry to produce life cannot occur in this atmosphere because of the presence of oxygen. So what we're looking for, if we believe in evolution, is there must be evidence that the early Earth's environment was much different than it is today, in order to allow the chemistry needed that can't happen right now. The reason the chemistry happens in living things is because we have DNA. It's the instruction program for how to make things work. There would have been no DNA at the very beginning. So there were 2 guys, A.I. Oparin, he was a Russian, he was a Russian biologist, and J.B.S. Haldane was a British biochemist. They were both atheists, and they independently came up with an idea about how living things could have come together in the first place. And then their ideas have been combined. It's called the Oparin-Haldane hypothesis. It's the most widely accepted scenario for the naturalistic origin of life. Remember, you need CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. So they said, let's see, what common gases could give us most of those elements? They said, well, methane, CH4, ammonia, NH3, water, H2O, hydrogen, H. Okay, so you got 4 of the 6 necessary elements. You don't have sulfur and phosphorus, but let's see if we could do anything with that. So they said that this mixture of chemicals, which was called the primordial soup, had to be struck periodically by some sort of an energy source. They proposed maybe lightning, or others said, how about ultraviolet or heat or shock waves? And this would have produced chemical reactions that formed amino acids, and then proteins, and then finally living cells. Well, is this reasonable? In order to test it, there was a University of Chicago doctoral student named Stanley Miller. He came up with an experiment where he mixed together those gases in various proportions, and This is the actual apparatus that he used. The Denver Museum got a hold of it. And so you had the gases in here, the methane, ammonia, water vapor, and hydrogen. And they were circulating around, and you had water in the bottom. So periodically, there would be a spark, and we'd see, hey, what do we have? Then this would cool it down, condense it, and it down at the bottom. After every so often, you would take a sample and see what's in there. Did you get it? Any living thing? Other experiments use varying sources of energy and maybe a variation, but they're all based upon Miller's design. So after a while, he found he had produced some amino acids. Okay, living things are made out of proteins, and proteins are made out of smaller chemicals called amino acid, not amine old acid, but amino acids. And so he produced some amino acids, and people say, we produced life in the lab. No, we produced amino acids. There are hundreds of different types of amino acids in nature, but every living thing ever studied has been made out of 20 very specific amino acids. Only those 20. Any other amino acid that gets in there messes up the chemistry. Put oxygen in there, you mess up the chemistry. You put fluorine in there, you mess up the chemistry. These are the 20 different amino acids that are used in proteins. It's called glycine, L-alanine, and all of these. So you ready for a test on this? L-tryptophan. You probably heard that the reason you get sleepy at Thanksgiving is because turkey has a lot of tryptophan. I don't think it has any more than anything else does. I just get sleepy because I had a big meal. So he was able to produce some of the amino acids, not all, but some of the amino acids. But life is more than just a few amino acids. I'm going to go over some of the problems with believing that life was a result of random chemical processes. One of the obvious ones is oxygen. Fluorine is the most reactive element there is as far as taking away electrons, but there's not that much fluorine around. But there's a lot of oxygen. The atmosphere is about 78% nitrogen, which is a pretty inactive gas, but it's 21, 22% oxygen, which is a really reactive gas. The problem is if you put oxygen with all of these other things, it's going to interfere, and it says, hey, give me 2 electrons, and it fastens onto something, and it stops the reaction from going any further. So what you have to do is deliberately eliminate oxygen from your experiments. Well, here's the problem. In the very lowest sedimentary layers of the earth, they're called Precambrian sediments, there have been what's called red beds. Red is a characteristic color of rust, okay? Various oxides, iron oxide, uranium oxide, and so forth. There have been red beds discovered all the way down, indicating there's always been oxygen ever since there was a crust of the earth. So this is supposedly billions of years ago, but the Earth's atmosphere seems to have always contained free oxygen. So the distributions of carbon, sulfur, uranium, ferric iron, ferrous iron, they react with oxygen, and their distributions are pretty similar in all of the rock layers, no matter what the supposed age, which would indicate there's pretty much the same amount of oxygen all the way down. There have even been Australian sediments that are dated to 3.46 billion years ago, which is about the time life is supposed to have occurred, that have the same amount of oxygen that modern rocks do, modern sediments do. So this would lead us to conclude that oxygen was present all along. Well, when I was talking to the chairperson of the science department where I'm subbing right now in biology, I told her, there are 4 things that I specifically disbelieve. I think they're wrong in the textbooks. This is one of them. The idea that the atmosphere used to not have free oxygen. The evidence indicates it did. Of course, another one, which we'll get to, I guess, in a week or two, would be the idea that the human embryo goes through all the stages of evolutionary development before birth. That's not true. And another one is the idea that we contain leftover structures called vestigial organs from an earlier stage of evolution, like the appendix, the tonsils, the tailbone, and so forth. And another one is the idea that the fossil record proves evolution, that it gives us mountains of evidence for evolution. All of those are false. So anyway, this one says there was no free oxygen present, and so that's why the chemistry could happen. Yeah, but the problem is that there was free oxygen. And also, there's never been any sort of a trace of this so-called primordial soup of methane, ammonia, water vapor, and hydrogen. Nobody's ever found that anywhere. So how do living things deal with oxygen since it's so reactive? One time I had a little discussion in letters to the editor in the paper where I pointed out about oxygen interfering with chemical reactions. And this guy, he was the science librarian at Tulane University, he said, well, then why don't we rust away? Because we have DNA. DNA, when a mixture of these chemicals reacts on their own, oxygen is going to interfere. It's going to produce other stuff too fast, mainly biologically useless compounds. But in living things, the chemical reactions don't occur on their own. They're guided by DNA, deoxyribonucleic acid. It's got the specific instructions. Okay, grab an atom of this, grab an atom of that, put them together. Never mind any other excess oxygen around. No, just get these two and put them together. But at the very beginning, how much DNA would have been present? None. We don't have life. So how are we going to have DNA? Okay, so let's suppose that somehow we can eliminate oxygen from the atmosphere. Okay, if we eliminate oxygen, we've just eliminated what layer of the atmosphere? What layer of the atmosphere is made out of oxygen? The ozone layer. Ozone is a form of oxygen. Why is it important that we have an ozone layer? When you go to the beach, what do they tell you to put on? Sunscreen, sunblock, because the sun's radiation is deadly to your skin. And this is even through our atmosphere. But the ozone layer of the atmosphere absorbs the deadliest radiation and converts it to a safer form of radiation. This is the deadliest form right here. It's a wave that has a wavelength of about 310 nanometers. It'll cook things in a fraction of a second. A typical single-celled organism would probably be dead in less than a second if it was exposed to that. And we're talking single-celled organisms at the very beginning. So we got a problem. If we have free oxygen, we can't get the chemical reactions we need. If we don't have free oxygen, then we have no ozone layer and stuff is going to get destroyed just as fast as it can form. So this is commonly called the oxygen ultraviolet dilemma. If you do have free oxygen, you can't do the chemical reactions. If you don't have free oxygen, you're going to destroy stuff as fast as it can form. Problem, right? I would think so. Of course, if you're determined that evolution must be true, you're going to just ignore the problems. Okay, and so we've got a nice apparatus that Stanley Miller designed where this stuff is going to mix together. It's going to get zapped by some kind of an energy source. He used sparks. Well, in nature, we're talking lightning, which is thousands of times more intense than that is. So the same energy source that, if it's lightning, that produced the compounds in the first place, the next time the lightning strikes, it's going to destroy them. It's going to have to, the chemical compounds are going to have to be removed by a trap that's isolating them from the energy source. Well, the problem is then you need them to combine further. So you need to bring them out of the trap, put them together so they can get a little more energy and combine further. Take them out of the way, wait until they're ready to come together and form more complex things, more complex compounds. And so we're going to have to keep exposing them, removing them, exposing them, removing them, exposing them, removing them, so they can develop into more and more complex materials. Let's see, where do we have a mechanism like that in nature? Oh, we don't. There's no such thing. In a laboratory, yeah. And then the atmosphere is mainly what gas? Nitrogen. Nitrogen is actually very unreactive. It normally occurs in the form of two nitrogen atoms that are held together in a triple covalent bond And that's a strong bond. You can actually use nitrogen as a fire extinguisher. It won't burn. But if you think about something like the drag racers, they use the nitrous fuel. What happens is in a factory, you separate the nitrogen atoms out and you put them with something else, nitrous oxide or whatever. And once you've done that, then you put them back in there and you give them a spark. And when the nitrogen recombines, you get a tremendous boost. If you ever see any of the drag racing movies, somebody flips a switch and in goes the nitro. Well, it's the nitrous fuel that was separated so that it would be useful. Well, okay, many of the major proteins of cells are major components of cells are proteins. Proteins are made out of amino acids, and the amine syllable indicates that it's got an amine group, nitrogen and a couple of hydrogens on one end. Well, where'd the nitrogen come from? On the early Earth, if we've just got an atmosphere with a lot of nitrogen, the nitrogen needs to be separated. It's called fixation. It needs to be separated in order to be useful, in order to form the ammonia, so that you can then form the amino acids. Okay, so what would fixate the nitrogen? Its natural unreactive form, N2, has to be separated into two atoms of N that can form amine groups. Somebody out there? Oh, okay. So what does nitrogen fixation? Well, most of it is done by bacteria. There's bacteria all over the world. They take in atmospheric nitrogen and they separate it out, and now it's in a useful fixated form. Okay, so at the very beginning, we're trying to make bacteria. Where are the bacteria to give us the stuff we need to make bacteria? Ain't no such thing. Well, is there any other source for energy that can fixate nitrogen? Yeah, lightning can do it, but not on a large scale. And so the lightning would have to strike at exactly the right place to make the fixated nitrogen, and then they got to churn around and get close to each other. And then the lightning's got to strike again exactly the right time, exactly the right place, but not too strong, because then it's going to destroy the things to make them combine into amino acids. And then later, the amino acids to combine into proteins, the lightning's going to have to strike again at exactly the same spot, at exactly the right time, at exactly the right strength to combine into more and more complex materials. Well, you know, if you want to say, I believe in Santa Claus, I believe in the Easter Bunny, I believe lightning would fixate the nitrogen, okay, you can. It's not part of science, though. Okay, and then I've mentioned this last time. It's kind of hard to visualize without actually seeing the thing, but you can have two things be a mirror image. So suppose you have identical twins standing there and one raises the right hand and they're face to face and the other one raises the left hand. They're mirror images. Okay. There are, of the 20 amino acids that are used in living things, 19 of the 20 can exist in mirror image forms. They're called optical isomers, or here's a good test question, enantiomers. What? Cells are made out of proteins. Proteins are made out of amino acids. 19 of the 20 can exist in mirror image forms known as the left-handed or right-handed form. The reason we say left-handed and right-handed, you shine a light through it and it polarizes the light. Like you got your polarized sunglasses. Have you ever taken your polarized sunglasses and turned your cell phone and all of a sudden goes black? Because light polarized in this direction and light polarized in that direction can't get through. Well, you can tell whether it's left-handed or right-handed by shining light through it. So far, every single cell, every single organism ever tested, ever reported on by anybody, anywhere, at any time, at any place, has used only left-handed amino acids. Now, a typical cell is going to have at least about 24,000 amino acids. Well, every single one of them's got to be left-handed in order for it to even be alive. Every single one of 24,000. Now, on the other hand, DNA, it's centered around a sugar called deoxyribose. It can also exist in mirror images, right and left-handed. In DNA, human beings have 3 billion base pairs centered around this deoxyribose. Other things have anywhere from a few million up to 100 billion in lilies. Everything that everybody has ever studied at any place, at any time, and ever written any kind of, I'm emphasizing here, every single one of the sugars in DNA has been right-handed. So I took a class one time on an ecology course, and I didn't want to tell the teacher, hey, I'm a creationist. I wanted to pass, you know. But I asked him, wouldn't it be a valid application of probability studies to calculate what's the probability you could get 3 billion right-handed sugars in a row without one single left-handed sugar? Wouldn't that be a valid application of probability studies? He said, oh, I guess so. It's off the charts. The DNA could be made of only right-handed amino acids, and proteins could be DNA right-handed sugars and proteins left-handed amino acids. You can do this with intelligent intervention. If you got really sophisticated equipment in a laboratory and you got computers helping to guide everything, but not by random chance out in nature with chemicals getting struck by lightning. Nobody's ever demonstrated any kind of a random chemical process that could make that happen. So this would be an example of mirror images. Alanine, the dotted lines indicate it's moving away from you. Okay, so the amine group is on the right-hand side moving away from you. In this mirror image, the amino acid is on the left-hand side moving away from you. It makes a difference. Some years back, in the 1950s, some drug company came up with a tranquilizer called thalidomide. I've mentioned this before. And if a woman took thalidomide and she happened to, a pregnant woman, and she happened to get one version of it, her baby would be fine. The other version, her baby would be born without arms and legs. It makes a difference. So how do we put together stuff like this? Nobody's ever figured out a way to do it. Even if they could, that would indicate intelligent intervention can produce non-random results. It wouldn't indicate that random chance produces non-random results. So let's say a cell just use one of the 20 types of amino acids instead of 20. So we just want left, 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 left. So let's say we have a cell that's put together out of 125 proteins, 100 amino acids, which is a really simple protein, a simple cell. What would be the chance of using only the left-handed form? Never mind the fact there's 20 different variations, just left-handed. Well, it would be about the same as flipping 12,500 coins at the same time and having every single one of them come up heads. That chance is about 1 in 2 to the 12,500th power, or 1 in 10 to the 3,760th power. That doesn't mean anything, just a big number. Well, the commonly estimated number of atoms in the universe is somewhere in the neighborhood of 10 to the 80th power. Suppose you had a bunch of machines. Each one flips 12,500 coins at a time, and you got 10 to the 80th power machines, and they're flipping 1 billion times a second for 30 billion years. So far, you would have had about 10 to the 26 power tries. We need about 10 to the 3,760th power to be reasonably sure it's going to happen one time. We have got a whole long time to keep these things flipping to be confident that we can just get all heads one time. I don't believe that. I'm sorry, I'm a little skeptical. Okay, so let's think about, we're trying to put together a living cell from a primordial soup. So we can't just put hydrogen, nitrogen, oxygen, and carbon in there. First thing we have to do is start with the right chemicals. You know, in living things, we also have phosphorus and sulfur at the very least. So we're going to have to start with the right chemicals. And then of those chemicals, they're going to have to come together into amino acids and sugars and bases in DNA or RNA. And then proteins are made out of hundreds and hundreds of these things. DNA is made out of millions or billions, so there's going to have to be hundreds or thousands that are going to have to overcome the natural attraction. Here's a positive, here's a negative. They just want to stick together. They don't know where they're supposed to go. So they're going to try to come together. They're going to have to somehow work their way past all of the useless chemicals in their way and then link into each molecule of protein and of RNA and DNA. Then, once they've linked together into a molecule of protein, one protein by itself, so what? A living thing's got a lot more than that. They're going to have to come together into clusters, commonly called coacervates. Then some of those have to attract the other molecules that they need. Okay, now we've got all this stuff together, but it's in a water environment. It's going to tend to just kind of spread outward. We got to put a cell membrane around it to hold it together and protect it. Okay, actually, the cell membrane can come together spontaneously. It's a thermodynamically favorable molecule. But then finally, when we've got all of this stuff together, it has to, oh, wait, it's not alive yet. It needs to come alive. So this is a cross section of a typical animal cell. It's unbelievably complicated. It's more than just a few amino acids strung together. Chemistry is not the solution to the problem. Chemistry is the problem. So as we got all of these things mushing around and swirling around and stuff like that, we're going to have some chemical problems. One, there are something called interfering cross reactions where the wrong stuff reacted. This positive said, hey, I see a negative, and just linked on. So that's going to stop anything useful from being produced. And then even with the primordial soup like Miller had with methane, ammonia, water vapor, and hydrogen, the problem is the chemistry is so complicated, people don't start from scratch. They go to a chemical supply house, which has got very sophisticated equipment, and they buy the 20 specific amino acids that they need only in the left-handed form. But even that is far too simple. 2 of the 20 amino acids require sulfur. We're going to have to throw sulfur in there. And DNA and RNA require phosphorus. And the very earliest living things, in order to manufacture some kind of food structure available for other things, are going to have to do something like photosynthesis. Photosynthesis requires magnesium. And then we need to get oxygen through our bloodstream. We use iron. Octopuses use copper. We use calcium for muscle contraction, for bones and so forth. So you're going to have to throw in all of these extra elements into your primordial soup. If you thought it was bad before, it's going to be even worse. So what's the probability we could form a cell? Um, Dr. R.L. Weissong, Randy Weissong, he's a veterinarian, and he did some calculations, and he figured out the simplest theoretically possible cell would be a little simpler than what I said before, 125, 100 amino acids each. He said, let's go with 124, 400 amino acids each. Okay, so if we have nothing but pure amino acids, we bought the right kind at the chemical supply house, no garbage compounds in the mix, the probability that the right ones could link together and form even the simplest cell would be less than 1 in 10 to the 78,400th power. So if there's as many types of cells as there are atoms in the universe, the probability is still less than 1 in 10 to the 78,300th power. So people say, well, it could happen long enough time. I don't care how many planets you have, how long you have, ideal conditions everywhere in the universe for trillions of years wouldn't help. Because even if you could put everything together, how's it going to reproduce? The reason that the proteins come together is because DNA has the information that says, hey, go get me an L-alanine and an L-threonine and an arginine and bring them all together in a specific sequence. They don't just come together randomly. They come together in a very specific sequence to form the components of living things. So it's not enough to just throw a whole bunch of amino acids together. Now let's get to the DNA. DNA is what guides the way things come together. One strand of DNA even in the simplest bacteria, what are considered the simplest bacteria, contains millions of these nucleotides that work in pairs, so we usually call them base pairs. They're represented by the letters A, C, G, and T, adenine, cytosine, guanine, and thymine. They can be arranged an infinite number of ways. Like you can write any book you want using the letters of the English alphabet. We have 24 letters, or using the Morse code, dot, dash, space. You could specify anything you want using those three characters, dot, dash, space. So we have the genetic code A, C, G, and T that's stored in here, stored in the DNA structure. The DNA is subdivided into smaller units called chromosomes. Normal humans have 46 chromosomes unless they have a genetic defect, very rare. Other types of organisms have varying numbers of chromosomes. And then the chromosomes are subdivided into thousands of genes. Each gene contains the instructions in code to make a specific protein, or to turn on and off some cell function, or to produce some type of bending for a certain structure. So the genes that code for production of of proteins, are divided into groups of three, triplets. They contain the information to put one specific amino acid into place. Okay, just to put together an E. coli bacterium, which is supposedly one of the simplest things, it would take 6 volumes of 300 pages each, just to write down the CCAT, CCGG, CTTA, all of those things. 6 volumes just to write the instructions to reproduce one bacterium. Okay, and they have, I don't remember if it's 2 or 3 million. Well, we have 3 billion. But then lilies have 100 million. Sharks have about 4 billion. Wait a minute, I thought we were the most highly evolved creature. We must not be. So here's what has to happen in order for things to come together. They're enzymes. Enzymes are proteins that have a specific function. They act like little molecular motors, and they're going either pulling apart or putting together things. They're molecular machines, and they make chemical processes happen billions of times faster. And it's not just there's one kind of protein, there's not one kind of enzyme, there's thousands. So people say, oh, you need to eat some protein. Well, what kind of protein? There's different, there's many, many, many different kinds. And then enzymes are specific things that cause chemical reactions to speed up. And it's so funny when you hear somebody say, oh, you need to eat apples to get the enzymes. You're not an apple. When you eat an apple, your body's going to break apart that apple enzyme into its amino acids and put it back together into people proteins and enzymes and so forth. So it's funny. People say, you got to get those enzymes. Well, you just need to take in something that has the right amino acids, and your body knows what to do with it. It's pretty well planned that way. Okay, so here's what happens. In the reproduction of DNA into a new cell, you need to have enzymes working. Enzymes speed up the chemical reactions. Oh, did my video just go off? Or am I still on? No, I don't want it to. Okay, now the screen went to sleep. I thought I had told it to wait for 5 hours to do that. Okay, so enzymes make things happen billions of times faster. Have you ever thought about why do you have to rush somebody to the hospital, a little kid, if they get a fever of 105 degrees? Enzymes are going like this all the time. Get them over 105 degrees, they break. There's another name for cessation of enzyme function. It's called death. If your enzymes quit working, you die. You need them to perform the chemical reactions. So without enzymes, life is impossible. And the instructions to make each of the thousands of types of enzymes are contained in DNA. Instructions to make enzymes in DNA. But DNA needs enzymes to make anything else, including itself. So DNA has to be present to make enzymes. Enzymes have to be present to make DNA. So what's the probability that they could have evolved separately by gradual changes in dissimilar mechanisms and then come together? Well, it's a matter of faith. It's certainly not a matter of science. I would think that this would indicate that the beginning of life had to be due to incredibly intelligent and careful intervention. Okay, and then here's another cutesy little thing. I've been going over this with the students in the biology classes that I'm subbing in right now. There are fatty substances known as phospholipids. They can come together spontaneously to form membranes. So we've got all of our chemicals together, and it produced proteins and all the stuff in a cell. Somehow it produced the Golgi apparatus and all of the vesicles and so forth. Somehow that happened. Yeah, just wave your hand, it happened. Okay, well, the whole thing is in a watery environment, and water tends to kind of make stuff flow apart. We've got to hold it together. So you need a membrane around it. And actually there are these fatty chemicals called phospholipids. They can come together. If you can produce them somehow, yeah, they'll come together. And they form a double layer membrane like this, where my fists are on the outside. Well, you can't, right there. That's my fist, that's my fist, that's my fingers. Okay, so these things can come together and they surround the cell. What happens now? Cell starves to death. If it's going to reproduce, it's got to take in more materials so it can produce more proteins and can produce more DNA like itself. Where's it going to get the raw materials? They can't get through the cell. They can't get through the cell membrane. These things are called phospholipids, which implies they have phosphorus. One of the key ingredients in DNA is phosphorus. They stop phosphorus from getting in. However, there's a really cool little thing that lets stuff get in. There are microscopic gateways all throughout the cell membrane at specific places that let specific substances in to exactly where they need to go. These are called ion channels or protein channels or permeases, and they let the needed substances in and out at specific places, exactly where they need to be. So if we need to make more DNA, we're going to have phosphates come in right at the manufacturing apparatus for the DNA. Why are they there? Because the DNA has the instructions necessary to produce them and put them in a specific location in the cell membrane. It's all just an accident though, right? So here are some of the problems we have with the idea that primordial soup would have been responsible for life coming together. First, you have to eliminate oxygen from the atmosphere. If there's oxygen there, forget it. It's going to interfere with the reactions. It's going to produce garbage compounds. Okay, and then if you've eliminated oxygen, you've also eliminated the ozone layer. So you're going to have the sun sending down its full strength ultraviolet radiation, specifically at a wavelength of 310 nanometers, which is deadly to living things. You need to have some kind of a trapping mechanism to pull the stuff away from the lightning that produced it, otherwise it's going to get fried the next time the lightning strikes. You have to find a way to separate the nitrogen out into a useful form, and then somehow you have to find a way to make every amino acid in every living thing left-handed, and every sugar in the DNA of every living thing right-handed. And then you're going to have to overcome all of these chemical problems. And to make DNA, you need enzymes, but to make enzymes, you need DNA. Which came first, the chicken or the egg? Actually, the chicken did, according to the Bible. Mm-hmm. But in this, you know what I'm talking about. And the fact that the cell membrane does not let stuff through that needs to get through. Well, that would point toward what? Initial complexity or initial disorganization where things just kind of came together on their own. I would think it would point toward initial complexity, which is creation. Okay? So far, so bad? Well, people believe that there's life in outer space. I don't. So when I tell people I don't believe in it, they say, that's just religious. Okay, you do believe there's life in outer space. That's equally religious. I believe that the Bible is right in this area, but it's beyond the reach of human testing. It's a religious belief. Other people say, well, there has to be life in outer space. It makes sense to them that the Bible is wrong in that area, which is beyond the reach of human testing. That's every bit as religious. There was an idea that was put forth by Sir Francis Crick. He won the Nobel Prize for his co-discovery of the structure of DNA. This stuff is so small you can't see it under a microscope. And if you put it under an electron microscope, you're going to cook it. So you can't tell much about it then either. But what you do is you beam X-rays through it and you see how do they bounce out. It's called X-ray crystallography. So he discovered that DNA is a double helix structure, like the threads on a screw. And he won the Nobel Prize for it. Okay. Dr. Crick refuses to believe in God. He recognizes that the conditions on Earth have never been right to produce life by purely chemical processes. So what does he say? Well, then, okay, I will bow down and worship God. He says, no, it has to come from outer space. There must have been some super advanced civilization in outer space that started life, and it sent seeds throughout the universe. And, sperm is the Greek or Latin word for seed, so it's called directed panspermia. That some super intelligent alien civilization sent the seeds of life throughout the universe, and when it landed on Earth, it began to evolve. And you'll see this in the movies a lot of times, like the Red Planet, and then even in an old episode of Star Trek where Captain Kirk met up with this Indian girl, and Spock explained to him that the reason there's so many humanoids throughout the universe is because of some ancient alien civilization that sent out the seeds of life. Okay, so this actually is behind a lot of science fiction. Why are there so many humanoids? Because we all came about as a result of directed panspermia. Well, I don't think there's anybody out there, but there's no observation to support that belief. So, in an attempt to avoid the conclusion that life was produced by unknown non-natural processes performed by an unknown being outside of nature, that is God, who did some unknown processes, they have to say that instead, oh no, life was not produced by an unknown non-natural process under the direction of an intelligence. No, life was produced by unknown natural processes under the direction of, okay, intelligent beings. So let's get rid of God and let's make it flesh and blood beings, because we're trying to get rid of non-natural processes and explain it by natural processes. This is religion, that's all it is. So as I mentioned before, carbon is the key to life. Out of all of the elements that exist in nature or have been manufactured artificially, only carbon is capable of forming the long chains needed by living things. And we've tried them all. Nothing else will form the kind of long chains. And anything, I need to change that to 118. When I wrote this, it's 112 was the highest one. Anything else, in fact, anything past atomic number 92 is highly radioactive, and they fall apart. The higher the atomic numbers, fall apart instantaneously. So the ones that are known to occur in nature, they won't form long chains. We've tried them all. And then the chemistry of life can occur without oxygen, without free oxygen, but it cannot occur without liquid water. You have to have something to bring in nutrients and transport wastes away. Water's got to be there. Okay, so you'll keep hearing that we've discovered another planet out in space, and I'll talk about that another time. I'm skeptical about all of them. But we've discovered another planet out in space, and it's capable of sort of supporting life. Well, in what's called exobiology, the idea that there's life out in space, there's something called the Goldilocks zone. Life can't exist without liquid water. And liquid water is one of the most common things in the universe other than hydrogen. The Bible says, praise the Lord, ye waters that are above the heavens. We pointed our telescopes out in space, and we've seen, oh yeah, there's the spectrum, the spectral signature of water. It's out there. It's all over the place. So if we want to have a living thing, we're going to have water in a liquid form. It can't be steam, it can't be ice. Can't be too hot, can't be too cold, it's got to be just right. So everybody knows what you're talking about when you say the Goldilocks zone. Any planet that's too hot or too cold, even if they are there, couldn't possibly have life. And then also, if the planet is getting too much of this kind of radiation, that kind of radiation, even if the temperature's not too bad, it's still going to cook the stuff. You know, if it's producing a lot of ultraviolet, the reason that the ultraviolet, the 310 nanometer ultraviolet kills stuff is because it's got exactly the right amount of energy to vibrate and break carbon bonds. So if something is out in space and it's alive, it's got to be based on carbon. But if there's that particular wavelength of light coming in, it's going to destroy carbon compounds no matter where it is in the universe. So life would be impossible on a planet that was too hot or too cold or had the wrong kind of radiation. Is there life in space? Well, this is what the Bible implies. It doesn't clearly say, no, there's no life in space. But it does say certain things. Genesis 1, verses 14 through 18 says, the heavenly bodies are intended to furnish light. They serve as signs, mark off seasons, days, and years. It doesn't say anything about anybody living out there. And people say, oh, we discovered another planet around a star that's 580 light years away. I saw that today. Okay, the closest star to us, a light year is how far light travels in a year. It's about 6 trillion miles. The closest star to us is Proxima Centauri. It's about 4.5 light years away. And when we point our most powerful telescope at it, the James Webb Space Telescope, you know what we see? A pinpoint of light. That's the closest star. So then, let's focus on something that's 120 times as far, 580 light years away, 120 times as far. What's it going to look like to us? A pinpoint of light. So they say, oh, we discovered this planet around us. How? How could you discover a planet around this star? I'll talk about that another time. But I'm just really skeptical about all these claims about planets around other stars and how they have hamsters. They haven't said they have hamsters, but you know, they have this kind of environment and so forth. I'm really skeptical about it. Okay, so Romans 5:12 tells us that through one man sin entered the world. Well, the Greek word is actually cosmos, which is the whole universe. And when sin came, death came. Romans 8 verses 19 to 22 does not say, well, only the earth suffers in travail. It says all of creation groans in travail because of what happened right here on this little planet. So if there are other beings out in space who never sinned, would it be just of God to subject them to decay because of something that they never did, that we did here on earth? Rhetorical question. But the Bible and science, second law of thermodynamics, both say that this tendency to decay extends throughout the entire universe. Well, the effects of Adam's sin go even further than that. The Bible tells us that his sin affected not only the earth, but heaven itself. If you read in Hebrews 9, 22 to 24, he had to take his blood into the Holy of Holies in heaven. It was so significant what happened on earth, on this planet, not some other planet, that the Son of God had died unto its effects. Deuteronomy 4:32, God was speaking to the Israelites. He said, from one end of the heavens to the other, he has never dealt with anyone the way he did with Israel. So he gave them an opportunity for redemption. Well, if the extraterrestrials sinned, God just said he didn't give anybody else the chance to be redeemed. Would that be fair? Then if beings on other planets sinned too, then the devil must have been planet hopping. He was here and he tempted this one and he went there and tempted that one and went there and tempted that one. So the question would be, were we the first ones that he tempted to sin, or are we just part of a long series? And then 1 Corinthians chapter 15 is often called the resurrection chapter. It tells us that the first Adam brought sin and death. The last Adam, Jesus, brought righteousness and resurrection. So let's suppose that some being on another planet, we're going to call him Zorblat. Zorblat sinned on that world. So the first Zorblat brought sin and death to that planet. Does Jesus have to go over there and be the last Zorblat on that planet? Well, if he doesn't, that's not fair. The Bible says he died once and for all. It doesn't say he died a bunch of different times. And then 2 Peter chapter 3, verse 10 says, when Jesus comes back to judge this earth, not only will the elements here melt with fervent heat, but even the heavens are going to be dissolved with a great roar. Big Bang is coming in the future. It's not a past event. So yeah, this earth is just a little tiny speck in the universe, but Ephesians 3:10 tells us something. Everybody's familiar with Ephesians 2, verses 8 through 10. By grace you're saved through faith, and not of yourselves. It is a gift of God and not of works, lest any man should boast. I didn't bring a Bible with me. It would be really beneficial to read Ephesians chapter 3. Anyway, do you have it? Okay, Ephesians chapter 3, starting in about verse 8 through 10. I'm going to do a little song and dance here while Anthony pulls it up. Ephesians 3.
Ephesians 3:10 through
Starting with about 8. Let's see what it says.
You want me to read?
Yeah. Okay.
It says, unto me, who am less than the least of all the saints, is this grace given, that I should preach among the Gentiles the unsearchable riches of Christ, and to make all men see that what is the fellowship of the mystery, which from the beginning of the world hath been hid in God, who created all things by Jesus Christ, to the intent now that unto the principalities and powers in heavenly places might be known by the church the manifold wisdom of God.
Okay, so the Bible tells us that God is showing off through us. The purpose of the church is to demonstrate the manifold wisdom of God to the principalities and powers in the heavenly places. Same book, a couple chapters further on, tells us who they are. That's the demons, the fallen angels. They were up close and personal with God. They saw him in all his, well, I don't know how much of his beauty and glory they saw, but they said, nah, we're not interested, and they turned against God. God actually knew that was going to happen. He sees the end from the beginning. So he set it up where there was going to be a different group, us humans, that didn't start out close to him. Down here on earth, Adam sinned and we started out away from him. And then God set a plan in motion that his son would come to earth to die for us, to show his mercy, his grace, his magnificence. And so the principalities and powers, the good angels and the bad angels, look at what God did for us and say, wow, dope. The bad angels, dope. The good angels, yes, we made the right choice. The bad angels turned away from God. The good angels stayed with him. So God is showing off to other beings besides just us humans through us. So how many planets does he need to do that? Just one, this earth. So just to talk a little bit about UFOs, most UFOs can be explained by natural causes like reflected light and secret military aircraft and so forth. Back in the 1990s, which is 20-some years ago, we retired the SR-71 Blackbird, which would travel at, I think, over 3 times the speed of sound. Boy, that thing had to be something going across the sky. Look at it go. We retired it. You think we don't have anything faster? I know people will say, well, we have satellites out in space. Yeah, but I think we probably have some classified military aircraft as well. And then people say, oh, Area 51, where the UFOs are. No, Area 51 is a testing base where they test new kinds of aircraft. A few years ago, Nancy and I went to one of the Naval Air Station air shows, and this was the first year that the stealth jet had been declassified. Previous to that, nobody could talk about it. So I got to talking to one of the stealth fighter pilots, and he said that they had had a crash in the desert in New Mexico a couple years before, and it was a stealth jet. And all of the news media was saying, oh, a UFO went down. No, it was a stealth jet. There's a whole bunch of classified military technology that you and I don't know about, but there may also be some things that can't be explained in purely natural terms. Remember, the Bible says Satan can make himself seem like an angel of light. When God allows it, he can interact with the physical world. He even does things to people's bodies. In the book of Job, God allowed him to put sores on Job's bodies. And then God even allowed him to pick Jesus up and bring him to the pinnacle of the temple. So when God allows it, Satan can do things to people's bodies. In the last days, he's going to deceive a whole lot of people. He makes people believe that UFOs have the answer to all our problems, and that means, oh, I don't need God. I don't have to repent of my sins. Let me turn to them instead of God. There have been experiments done by human hypnotists where they'll get permission from somebody and they say, I'm going to hypnotize you, implant a false memory. And they do this. They hypnotize a person and say, oh, you were on a picnic with your Aunt Sally when you were 7 years old and you're eating potato salad next to a brook, and it never happened. But when they bring the person out, that person remembers that. If you gave them a lie detector test, they would say, yes, I was with Aunt Sally. I remember that clearly. And they do remember it. It's a deceptive memory. Well, I've showed a video here at church called Alien Intrusion, and if human psychologists can do this and make you think something happened that didn't actually happen, do you think the devil couldn't do the same thing? There have been so many UFO movies down through the years. So there was one, Fire in the Sky, where these guys say they were taken on board a spacecraft, and they really believe it because the false memory was implanted. But think back to the reports that came out about 80 years ago, UFO reports, little green men in flying saucers, right? Well, now the reports are these ships capable of incredible maneuvers, and the aliens look like that. So either the aliens and their ships have evolved a tremendous amount in the last 80 years, or else Satan knows, okay, what will they swallow? And he always gives us, like 2 steps ahead of current technology so that we'll believe it. In that video, the alien intrusion, which I recommend if anybody wants to go look that up, I don't remember who it's by, but look for alien intrusion. The people doing the video interviewed a bunch of people that had had encounters with aliens. And normally, I didn't know this, when it happens once, it's going to happen again and again and again and again and again. And so the people reported having been taken away by aliens, they lost consciousness and they awoke and they had the memories of all of this stuff. And then several of them got saved. So they became Christians. And the next time the so-called alien visitors came back and were going to do stuff to them, they would just crowd, Jesus, help me! And the aliens would screech and disappear. Why would an alien who's flown across a galaxy be afraid of the name of a carpenter who lived 2,000 years ago in an obscure village of Galilee? I think because he is who he said, and they are not who they say. The so-called alien visitors are demons. It's a demonic deception. Okay, and just a couple of more things about the idea that aliens could come visit us from out in space. The nearest star, called Proxima Centauri, is a little more than 4.4 light years away. That is, at the speed of light, it takes about 4.4 years for light to reach us, and radio signals and all of those things, they all travel at the same speed. So if you watch the movies, you'll see somebody goes into a wormhole and they come out in a different part of the universe. It's science fiction, it's not science fact. We've never detected any such thing. Black holes are out there, and from what we can tell, when something goes into a black hole, it just gets crushed. It doesn't come popping out somewhere else in the universe. So for the aliens to reach us from the nearest star in this amount of time, 4.4 years, they would have to accelerate from rest in their frame of reference up to the speed of light, and when they got here, they'd have to decelerate. So the formula for energy Kinetic energy is 1/2 mv squared. So if you take just a little car moving at 60 miles an hour, about 1,000 kilograms, a ton or so, that has about 450,000 joules of kinetic energy just traveling at 60 miles an hour. But let's try to get it up to the speed of light, which we don't know of any way to do that. Theoretically, you can't get matter to the speed of light. But anyway, if somehow you could, let's say we have an alien ship that's only the size of a small SUV. Not a big giant thing. Okay, to travel at the speed of light, it's going to have 100 trillion times as much energy as that little car going along at 60 miles an hour. That's to get it up to the speed of light. That amount of energy is 300 times the amount of energy that reaches the Earth every second. 300 times that. So when they got close, they're going to have to decelerate now. Well, when you stop your car, you step on the brakes, and the kinetic energy is converted to heat. That's why you don't touch your brake drums after your brake discs or brake drums after you stop. Those suckers are hot. You got to put out a tremendous amount of heat. The kinetic energy is converted to heat. Okay, here are these guys coming from some star out in space at the speed of light. Now they got to get down to 0 as compared to the Earth. Where'd that energy go? Now people will say, well, maybe they have developed this technology. Maybe. That's not science, that's faith. All of this is expressions of faith. And if they wanted to go back, they're going to have a pretty big gas tank, right? To be able to get up to the speed of light again. And, people say, well, maybe you could do that with antimatter. Maybe, perhaps, could be. It's not science. It's science fiction. And then one of the best arguments against visitors from outer space would be something that's called SETI, Search for Extraterrestrial Intelligence. Ever since the 1960s, there are scientists who strongly believe that there's life out in space. They've been searching the skies for radio signals from space, and so far, how much success have they had? 0, not a bit. There have been billions of dollars spent and billions more planned. So if the aliens were already here, who would it make the most sense for them to contact? The people that believe in them, that are looking for them. They've had 0 success. Well, I really suspect that it's because there ain't no aliens out there, no flesh and blood aliens. Why would there be flesh and blood aliens? Well, if you believe in evolution, you believe that when the conditions are right, life will arise spontaneously. I don't believe that. Based upon all of the chemical problems, the biochemistry of it, I would say life can only exist where God wills it to exist. And we know He willed it to exist on this planet because we're here. But I don't see any biblical reason, any scientific reason why God would have willed there to be life out in space. And another time we'll talk about problems with believing that there are planets out there that could support life. But I think that's good timing. It's 2 minutes to 8, so we've been 2 hours. So next time I'll start out with a quick review of what we went over. And then we're going to get into biology and cells and DNA and reproduction and all of that kind of stuff. So, okay. Those watching the video, we're about to try it and see if it worked. I sure hope it did.